I'll give it a sec. Will I be able to, will it be a red dot or something, or?
Yep, you're good. You're live.
We're good. Okay. Welcome everyone. ELEC2134 Midterm Crash Course. If you're all ready to learn what? At any point you can interrupt me, ask a question. If you think I've done something wrong, just let me know. And yeah, let's take it away. Okay, here we go. So this is what we're going to be doing today. Wait, is it? Oh yeah, frozen.
What's that?
Is that on? There we go. Okay, we're going to go through 6 topics today for your crash course. I'm going to be doing the first 3. My name's Josh. Jackson is going to be doing, well, the first 2. Otto's going to be doing the 3rd one, and Jackson will be doing the last 3. So yeah, like I said, at any point interrupt me, put your hand up if I've done something wrong, if you have any questions. All good? Okay. Let's start with AC power. Okay, I'm just going to go through some notes. This should all be familiar to you. And yeah, I'll just go through it. So if you remember in ELEC Pod 1, you had power, right? You might have even mentioned complex power, but we're going to deal with it a lot more in this subject. Okay, so this is our formula. We've got it all in complex form. Everyone remembers phases. We've got a phasor S, complex number, that's equal to half the voltage, which is also a complex number, and I, and everyone knows what this means. This is the conjugate. Wait, there we go. We've got the conjugate, and this represents our complex power. Now, this S is really useful. If you find this S, you can basically solve almost any complex power question. We've got 2 representations for S, as you probably know. We can write it like this. Oh, that's messing up. Oh, okay. We can write it as average power, and this thing, the imaginary power, and we can also write it in our other form, our mod arg form, which tells us some other stuff, but we'll just go through some examples, okay? Be very careful of the units in the test. This trips a lot of people up. Remember, this is I've seen a lot of people get tripped up by this. Volt amps versus volt ampere reactive, 2 different units for 2 different measurements. Yeah, have a quick look at this. Any questions? Pretty good, okay. I beg your pardon? The slides? We'll post the slides after, or?
We might post the slides after the whole session is recorded as well, or via YouTube.
Okay, yeah. So this triangle, you've all heard of it, the power triangle, very useful. You're going to be using it in a lot of your problems. Leading versus lagging, something to remember. It's actually pretty simple once you get your head around it, but it can be really difficult at the start, like it certainly was for me. So if you have S, right, and you have theta being positive, you've got an inductive load, and the nature of the load is lagging. If you've got theta less than 0, it's leading, and it's capacitive. Okay, any questions there? No? Okay, we'll move on to an example. Okay, so we're asked, when you're going through questions, definitely highlight key things. Okay, let's look here. It's given us V of t, right? Here we go. There we go, V of t. It's given us I of t. The first thing that jumps out to me is these are both cos. Can somebody, does people know what will happen if one of these was a sine? Yeah, correct. So it's really nice, this question's being really nice to us. It's given us 2 things in cos. So when we turn them into phasor, we can do it really simply. Okay, let's solve for the power factor. So we've got the formula. Let's look back up at our notes. Do we have a formula for power factor? Well, it's cos theta, right? Now, there's a really simple way to do this, but I'm actually going to take a bit longer of a way, and you'll see why in a second. So if I figure out S, and then I find the argument, right? I just have to take cos theta of that to find the power factor. Pretty straightforward. You could just subtract the angles, but you're going to see what I'm going to do. So let's turn it into phase representation. Okay, so V is equal to 300, angle is 30 degrees, I is equal to 15, 15, angle is minus 28, okay, minus, is it because I'm touching the thing? Yeah, it's because I'm touching, okay, I'm going to be careful. Okay, that's better, minus 25 degrees. Okay, we're going to take I star, and this is going to be represented as 25 degrees, and we're just going to put it into the formula, as simple as, the formula for S is equal to a half V I star. Really simple. You should remember your laws for complex numbers. You should know them off the top of your head. You should just be able to do it, because it will make your life easy. So if you remember, when we multiply complex numbers, we add the angles together. So we get 55 degrees. And then what we can do is we can just multiply these two numbers. Does anybody know what 150 times 15 is off the top of their head? I think it's this, but I'm not sure. Yeah, okay. Okay, it's now asking us our power factor. Now, that's going to be the cos of the angle. Really easy. What's the angle? Can somebody tell me the angle here? Did we just pick it out? That's correct. Easy. Now, there was an easier way of doing this. You could just have looked at these, subtracted this from this. But for the next step, you're going to see why I have done this. Okay, you put this into a calculator. Does anybody have a calculator on them? Somebody can just read it out. Yep. Make sure it's in degrees. 0.57. That seems to make sense. 0.57. Okay, and that's our answer. All right. Now, Now, the reason I did it this way, why I found S. The reason I found S is because it makes our life really easy now. Can somebody tell me, in terms of S, how we can find the average power absorbed if we already have S? Yeah?
It's just the real part?
It's just the real part. Exactly. So we just take the real part of S. Wow. I've got to get used to this. The real part of S, which is going to be just the real part of 2250, 55 degrees. Does anybody have a complex calculator and can put that in? Oh, I'll do it.
1291.
1291. And can somebody remind me what the units for that would be?
Watts.
That is correct. Always be careful of your units. This is going to kill you if you don't. So I'd recommend remembering this table, test it with a friend, something like that, and just remember which unit goes where. VA and VAR are the obvious culprits. Okay, maximum power transfer. Now, this is the next step. Okay, here are our steps, right? Everyone remembers V Thevenin and Z Thevenin from ELEC Pod 1. So exactly the same as that, right? For the first step, we just have to find V Thevenin, Z Thevenin. The next thing we do, so if we have a circuit here, we found our V Thevenin, our Z Thevenin. The way we maximize, so let's say it's asking us, how can we get the most power out to our load, given that we have a complex load? So we have a load that can have an impedance. What we'd do is we'd just set this, right? We'd set the load to Z Thevenin star, which is the conjugate. Now, it's pretty, I'm not going to harper on too long. I don't want to waste too much of your time. We do the exact same thing for, let's say we had it asks you put a resistor in, you want to get the most amount of power to that resistor. What you're going to do, you can't cancel out the complex part, so what you do is you just set it to the modulus of Z Thevenin. So you'd create a resistor, you'd figure out what Z Thevenin is. Okay. and you'd have a resistor with that many ohms. Easy peasy. Not easy peasy, sorry. It's hard sometimes, and especially hard. Should you remember these formulas? This is a question people get a lot of times. If you are good at remembering formulas, do it. If you're not, what I recommend you do is you just read or write it. It's really easy. It's a simple equation. You just use your V, you just use the normal VI star power equation. Okay, let's do our next example. Okay, we've got a bit of work cut out for us here. We have to find Z Thevenin. So I'll let you guys work on that while I do this. I'll get this up. Here we go. Yeah. All right. So let's find V Thevenin, Z Thevenin, our first step. So that's our first step. We're going to find V Thevenin and Z Thevenin. That's a pretty, from these points, that's a pretty normal problem from ELEC Quad 1. Let's just do it, okay? There's a few ways you could do this. What I'm going to do is I'm going to do a voltage transform, a source transform of these elements. I'm going to add them in parallel and turn it back, and it kind of already looks like a V Thevenin, Z Thevenin environment. Okay, let's do it. The first thing I'm going to do, let's do a source transform. The source transform thing is Vs divided by R, or Z in this case. Let's do that. We get something like this, 100 ohm, 100J, ohms, 100 ohms. I'm not going to draw the rest of the circuit because we can do that all afterwards. We'll just put a dot, dot, dot here. And can somebody tell me what this would be, what the source, how do I do? Okay, wait. Can somebody tell me what the source, just based on this formula, will be? You don't have to recalculate it all, keep it nice. Oh yeah, that is true. That's a good catch. Yep, turning into a current source. And can somebody tell me what it will be, what the value of the current source will be? Anybody? Yep, on 100J. Too easy. And what we can do then is, yep, turn that into minus J. That's quite nice, isn't it? We'll do a similar thing here. We'll add these and make a Z. We'll just say 100. We'll keep it easy. 100J, 100. And we'll redraw our circuit. I'm going to do a preemptive another source transform. If we're turning minus J by this value, using the same formula as usual, 100J times 100. Parallel, sorry. With 100, and then we will redraw this circuit. So we have 100J parallel with 100. We have our other components, which is 50 ohm minus 25J ohm. And we have our load over here, which we don't really care about right now. Okay, so we know V Thevenin and Z Thevenin here, right? It's kind of falling out of our source transformation. Okay, so what would V Thevenin be in this case? And let me know if I've made a mistake, because it's easy to make. Yeah, just the source. That's right, Otto. Let's go. Parallel with 100. And then Z Thevenin is equal to 100J, parallel with 100, plus 50 ohms, minus 25J. Okay, does that make sense to everyone? Any questions? Okay, the next part of this question is actually, let's look at our steps. It's asking us, the load can have any complex value. This should jump out at you right now. We have Z Thevenin, we have Z Thevenin, and we are just going to substitute ZL as Z Thevenin conjugate. Okay. So we'll say ZL is equal to Z Thevenin conjugate. Can somebody put that in their calculator? Everyone knows how to do this parallel thing? Everyone knows what that means. I don't know. Yeah? Can somebody give me both of these in complex form? Just
VTH is minus 50 plus 50J.
Easy.
And I think ZTH is 100 plus 25J.
Sorry?
ZTH is 100 plus 25J.
Those are nice numbers, which convinces me we're on the right track. Okay, can somebody tell me what ZL will be then? It's pretty easy. 100 minus 25J, that's correct. Now, what we could just do at this point is the last step. Let's find PL max. So I'm just going to use the formula, but if you don't want to use the formula, you just put this in a circuit. You could find the current and do half VI star. If you use the formula, which is reasonably non-obtuse here, we'll sub that in. Okay, an eighth V Thevenin squared divided by RTH. RTH here is just this part of the impedance. So it says 8 times RTH, that's easy. So yeah, 100, so we get 1 on 800 times, can somebody give me the magnitude of V Thevenin squared, or just the entire expression? So the entire thing is 70.7?
Just the magnitude of V Thevenin squared.
Yep.
5,000.
5,000? Is that V Thevenin?
V Thevenin magnitude squared.
Okay, yeah. So that's 5,000 over 800 is equal to 50 divided by 8. And we can put that in. Divided by 4, which is, what, is it 6.125? What?
6.25.
6.25, okay. There we go. 2, good. Just falls out. Okay. And now the load must be a pure resistance, II. Here we go. We just follow the step. Recall here, we set RL equal to the magnitude of Z Thevenin, which is just the magnitude of this. Can somebody give me that? Or 103 ohms. And what? Sorry, I almost forgot. I was just checking you guys. What's the units for PL max? Yeah. Okay. Let's go to the next section, transfer functions. Something entirely new. Let's move on to them. Pretty simple. We have an input and an output out of our transfer function. And when we choose that input and output, we take the division of the output divided by the input, and we define that as our transfer function. Okay. Steps, it's actually similar to ELEC Quad 1. You haven't done it exactly, but you've all done circuit analysis before. You all remember mesh, nodal, all that stuff, superposition. You can use any of these to find this expression. Okay. Here we go. where I'm quite fond of source transformation. So what I'm going to do is I'm going to create, I'm going to source transform this. So this is how I'm thinking about it, by the way. I'm looking here. I want to find this in terms of this. It wants me to find V out in terms of V in. So for that, I want to find V out in terms of V in, like that. That's what I want to find, right? So how am I going to do that? What I will do is I'll do a source transformation with this element over here. Got to stop doing that. And then what I'm going to do is I'm going to do a current divider, find the current through here, and multiply it. You don't have to do it my way. Mesh analysis is also a really good tool here. I just don't like dealing with simultaneous equations, so I prefer using source transformations. Here we go. Let's do this. We get this. It stays as VI because we just multiply by 1. We get 1 ohm here, 1 ohm here. And remember over here, we've got to convert this into, so this is the first thing you should do when you look at anything. I did some bad practice there. You should first turn every single element into its complex version. So does anybody know what the formula is for ZL?
JW.
Yep.
So it's just JW.
Yep.
These numbers are great.
Amazing numbers. I hope you get these numbers this nice in the exam, though I doubt Inla will give you that. So we get JW over here, and we get 1 ohm over here, plus minus. Okay, current divider. So what we're going to do is we are going to find the current running through here. We will do this. I'm just going to, so current, we're going to call this I or something. We'll say I equals, it's going to be 1 on 1 plus J omega, and then 1 on 1 plus 1 on 1 plus 1 on 1 plus J omega. All right. What I'm going to do over here is I'm going to realize that times VI. What I'm going to realize here is that this V out, right, is equal to 1 times the current going through it, Ohm's law, and we're going to say.
Josh, isn't it the other way around for a current divider? It's the one we want on the bottom.
I don't think so. No, I think it's just, it is. It's the one we want on the bottom.
Voltage divider is the one we want on top.
You put all the resistances that you don't want on the numerator.
Yeah.
All the resistance you don't want on the
So it
numerator.
would be 1 plus 1 on the numerator.
I'm pretty sure. No, I think this works. I'll do it that way. I thought you could do.
It's flipped for current that is.
Oh, it's been too long. Okay, wait.
Good catch.
So wait. You're saying that it's a good lesson. Revise. You're saying it's like this. Is that what you're saying?
You got your, instead of the 1 over 1 plus J omega on the numerator,
Yeah.
the 1 on 1 plus 1 on 1.
Okay.
The denominator stays the same. It's,
Thank you.
yeah.
That's a good point. Okay. Let's do all that. All right. 1 on 1 plus 1 on 1. Okay. Equals 2 on 2 plus 1 on 1 plus J omega equals 2 plus 2J omega over 2 plus 2J omega plus 1. I don't think so, because that should give me the answer. Wait, let me just stick with my method for a sec. I'm pretty sure, because this becomes 3 plus 2 on J omega times VI. See that?
Okay.
I'm not sure, unless I stuffed up somewhere else.
I think if you're working with like the admittances, that works, right? Because that's like y of the thing you want over the sum of the y.
Yeah, that's how I was thinking about doing it. Okay, I'm going to come back to that in a minute. I'm pretty sure this works. This is the way I did it in ELEC, and it unless I've been doing it wrong, it's all been cancelling out.
I think it makes sense if you just change that I to a V naught, like where you've written I equals that massive fraction times VI.
This I to a V naught?
Because then you just have...
Yeah, this I called this I, sorry. This is my I.
Okay. Alright, never mind.
Yeah.
Yeah, you're good.
Okay. Hopefully that didn't confuse anyone. Does anybody have I can redo a current if I've confused somebody. Everyone good? No? You want me to go back through the example? Yeah, I can go back through the example. Okay. Are you good up to this step over here?
Yes, I am.
Okay. If my current, do you want me to turn it all into impedance, into whatever, Y's, and then do it? Do you think that'll be easier? I'm happy to, this is the way I usually do it, which is, I take it as, this is the one you want, and then you do this. This is the way I usually do it. Is that right?
You do REQ on 6.
Okay. I'm just going to teach current dividers the way I know them. I'm pretty sure they're right. Okay. Over here, we have a current divider. We have 3 elements in the current divider. We have this element over here. We have this element. And we have this element, which is the addition of these 2 elements. Right? And we want to find this current. We're going to call this I. And the way I'm going to do that is I am going to use a current divider. This VI over here is actually a current. It's just that we're using the symbol because we did a source transformation. So what we can do is we can say this I, we just use a normal, what's the current coming out of here? It's VI. We, on the numerator, we do 1 over the thing we want, which is this component. And then we do 1 on the rest of the components. What we do then is we get 1 on 2, 1 on 1 plus j omega, just to take it slower. And then we get 2 plus 1 on 1 plus j omega. What I do next is I'm just going to times the numerator and the denominator by 1 plus j omega. And we get 1 over 2, 1 plus j omega, plus 1. And then what we end up with is we get 1 over 3 plus 2j omega. And that should be what we wanted to get. Good now?
Validated. It is correct.
It is?
Just to validate the method, you do I times REQ over your desired resistance.
Yeah.
Yeah.
Okay. Thanks, Otto. Okay. Sorry, that was longer than it should have been. But yeah. Okay. Just very quickly, there's 4 types of transfer functions. You usually don't have to worry too much about this, but I'm not going to say that because if I say that, I'm just going to put it in the midterm. So look at these, kind of know them. So it might ask you to find the voltage gain, the transfer admittance of the circuit, etc. Yeah, just have a look at that. Okay, plotting frequency response. I always didn't really like this topic, but we have to do it. It's in our course. Here's your steps. Find, if you have h of j omega, you find 5 j omega, which is, ooh, I'm not liking this iPad too much. Here, we find 5 j omega and magnitude of h of j omega. Everyone knows what that is? I'll just assume everyone does. Yeah. We just have to substitute some key points in. You almost always figure out the 0 point and the limit as it goes to infinity, and then just do another point. Usually it doesn't matter too much what point this is. However, it is useful over here. I've written this over here. To do one that kind of makes your algebra easy. So can everyone kind of see why I would choose omega equals 1 on RC here? It kind of lets you cancel stuff out. I like to do that. I try to make my life easy. Yeah, okay. let's do the example. Okay, the first thing we're doing over here is it says, let's read each step. It's given us a resistance, a capacitance, and it asks us to first derive h of omega. Now, in some things they do h of j omega, some things they do h of omega. I believe INMA wants you to use h of j omega, but it is kind of just conventional. Don't really worry too much about it. It's asking us to find V out over V in, and it says label at least 3 key points. So this is a 5 marker. They're asking us to find this first. We're going to get some marks for the 3 key points and for the correct amplitude and phase spectrum. So the amplitude, we want to plot h of omega or h of j omega, and we want to find the phase spectrum, which is going to be the angle of h of j omega versus omega. Okay, so why don't we figure out this quickly? H of j omega is going to be equal to V out over V in. This is what we want to find. Okay. Next part, we are going to use a voltage divider. Everyone remembers the basic voltage divider? Take that as a yes. We're going to rewrite our circuit first. Okay, plus minus 1 ohm. Everyone remembers the formula for capacitors? 1 over j omega, C, and C is 1 in this case, and we want to find V out. Okay, our V out, we use voltage divider. V out equals V in multiplied by 1 on j omega, 1 plus 1 on j omega equals 1 plus j omega plus 1. I just multiplied the numerator and the denominator. And now we can easily find our h of j omega, V out divided by V in equals 1 plus 1 over j omega. Any problems there? Good. Now the next step is going to be plotting. So what I'm going to do is I am going to set up this plot. This is how I'm going to do it. I'm going to first find my 3 points. I'm going to find h of j omega, right? Now, what have they given us omega as? Can anybody find it in the question? No. That is because you're plotting it as a function of omega. Okay, let's find the magnitude. This is going to be equal to 1 on 1 plus j omega, amplitude, and this, using our known rules, is equal to omega squared plus 1. Easy. H of j omega. Now, this is going to be the angle of this, right, minus the angle of this. So we will find that it is 0 minus the arctan of omega divided by 1, which is equal to the minus arctan of omega. Does that make sense to everyone? You need to know some basic complex number rules for that. All good? All right. Now, we're going to plot these first by plotting some points. Okay, let's put our points in. We're going to choose omega equals 0. I like to write it up as a little table. I'm going to choose magnitude. It will make it very clear to the marker that you know what you're doing if you make clear, concise things like this. And even if you make a mistake, they kind of know, okay, they're on the right track. Here we go. So omega equals 0. Let's sub that in. We get This becomes 0, this becomes 1. Let's do omega equals, what's a good point? Can anybody think of a point that might make our lives easier? 1? That's right. And we'll go omega goes to infinity. Okay. Now, can anybody tell me what minus arctan of 1 is?
45 degrees.
That's correct. It's not 40.
Negative 40.
Yeah, negative 45 degrees. That's correct. Okay, let's do the next ones. Oh yeah, sorry, I put it in the wrong thing. Can anybody tell me what minus arctan of 1 is? Sorry, minus arctan of 0.
Must be 0.
Yeah, nice. And if we do omega equals 1, we'll get 1 on root 2. And as omega goes to infinity, can anybody tell me what this will reach? Anybody remember how to do that? That's right. And we will also do this. Can anybody tell me what this will go to? That's correct. Nice. Okay, let's plot our graphs. Let's draw. There's a few things you should remember when plotting your graphs. It's good to line them up. So if you have two different graphs, it's good to line up your graphs like this. You want to write your units. So I'll have omega here. Ooh, there we go, omega, omega. I'm going to plot my angle here. So we'll say angle of h j omega. And over here we'll have the magnitude. All right, let's plot our points and connect the dots. Okay, 0. So let's plot on this one first. Let's do this. We'll make this 1. We will plot the next point, which is omega equals 1. We'll put it around here, and we'll trail it off over here. Okay, omega equals 1 equals 1 on root 2, which is around 0.707. So it's around here. And we'll plot our last point, which will go here. So we should label all our points. Let's put this over here. This is 1 on root 2, and this is omega equals 1. Right? We should write as omega goes to infinity, magnitude of h j omega goes to 0. And then we just kind of have to connect the dots, which will look something. You should kind of have a familiarity of your points, of how it should look. It looks something like this, and we just write there. Okay? Everyone good with that? You'd make it look a bit neater than me, and you'd use pencil so you can rub it out. That's pretty good. We'll do the other plot very quickly. We'll do our omega equals 1 point, and it will be minus 45 degrees. So we'll write our points here, minus 45 degrees. Make sure to draw your points. You're leaving marks on the table if you don't do this. Okay. We will label omega equals 1 again. Connect these. And we will just do this. Something like this. And then we have an asymptote. We should draw our asymptote in over here. Not a very nice asymptote, but we'll do. And it just goes like that. Gets closer and closer, never reaches it. And we say, as omega goes to infinity, omega goes to minus 90 degrees. Okay, I think that's it. Yeah. Otto, you want to take it away?
Let's do this. All right. Round of applause for Josh. Thank you very much. Fantastic stuff. All right. And okay, let's get a little setup. Okay, so we got resonance. So probably one of the most math bashy topics, as you guys might find in Lab 2, might have found in Lab 2, I correct myself. Let's go ahead and we'll run through a fair few content points just before we get into 2 of our questions. So let's do this. So if our circuit has an impedance given by this, the resonance condition is when our imaginary component goes to 0. Okay, and this is, it can be a little bit strange at times. You might sometimes have your impedance expressed as an admittance. So that's to say you have, I forgot the specific things, but you say that your y thingy equals 1 on r plus j 1 on, it's not meant to be 1 on r, it's 1 on g plus 1 on y or something like here. Sometimes they do that and you say, still, imaginary part goes to 0, okay? That's the entire point of resonance. If we go ahead and have our imaginary impedances cancel out to 0, something really, really cool happens between our inductors and capacitances in the circuit. I won't delve too much into that, but let's go ahead and do this. So resonance condition, there must be some frequency whereby our imaginary component of our impedance cancels out, all right? You'll see 2 to 3 certain types of resonance circuits in this course. Most typically, you have your series and your parallel circuits. However, INMA does like to test you and may include a hybrid example where you'd have to go ahead and work out all these special factors on your own. So, first up, we got resonances. So, series resonance, what we do here, we understand that R, L, and C are all in series. And so we go ahead, resonance condition, imaginary components, sum to 0. We get resonance frequency of 1 over square root LC. Okay? So moving forwards, we can also talk about resonance power. So this is just the power supplied by the source at resonance. Something important to talk about when we talk about resonance circuits is in comparison to our power factor stuff, okay? Something that some students get tripped up on is way back, I mean it wasn't way back, it was a couple weeks ago, you end up with, wow that was messy, you end up with your Thevenin-like circuit, something like this. This is your load, this is something to do with your source, I'll just put our source and your source, okay? Power factor, we were talking entirely about this thingy on the right, okay? You'd analyze the voltage at the output and you'd have your fun there. However, with resonance, we're talking about the whole thing. We're looking at it from the perspective of the source, right? So it is a little bit different, and it means that when we start talking about, how about I think we mentioned power factor a little bit later in the slides, but when we talk about this, we want to make sure that, okay, all impedance seen by the source disappears, right, at a certain frequency. So let's keep it moving. Second up, we got parallel resonance. Resonance occurs, funnily enough, again, at the condition of 1 over root LC. You will see that the imaginary component of our admittance, that is what goes to 0 here. Either way, our imaginary component disappears, okay? There's still some real component, which math does not break away here, don't you worry about it, but that is how these things work. Once again, power works the same at resonance, imaginary components disappear, all right? Let's do this. So, series and parallel, it's really just when we consider Z and Y in our formula, okay? That's really the only difference, but in any case, you should see the imaginary component of your transfer function or anything of the sort disappear at a certain frequency. We all happy with that? Good to hear. All right, let's do this. So, moving forwards, we got magnitude responses. I mean, rather self-explanatory. There are a couple extra features that we look at in terms of AC resonance, specifically bandwidth and its relation to our Q factor. And yeah, so bandwidth you define by half power points. And so that's given when your voltage hits 1 on root 2 of the resonant voltage, okay? Not too much to yap on there. We have definitions of bandwidth. It's really just the region, well, rather the size of the region at which you get significant flow of your power, which is this top cap. And yeah, all right. There are methods we may use to determine what our half power frequencies are. That may come in handy a little bit later, but yeah, a little more content. Q factor, it really is, I guess, graphically your indication of how selective a filter is, okay? And what I mean by that is if you have a very tiny bandwidth, it only picks out a certain number of frequencies if you use that as a transfer function. More relevant in later years, but it is a very nice indicator for the shape of your graph, right? And also it indicates that if you have a high power factor, your peak looks very symmetrical, which allows us to use our Q factor approximation of our upper and lower power frequencies. All right, anything else? There are a couple ways that we can assume immediately what a power factor might be, but I mean, it shouldn't be too necessary for our calculations in this course. We can always brute force it, and quite frankly, that's what we're going to do right now. Okay, so first things first, let's take a peek at the 2024 Term 1 midterm. This is question 4A, and let's just run through it. So first things first, as they usually come, we got question A, first question you would have seen. We go, let's just do it. AI, derive and calculate the resonant frequency. We've got our circuit, it's all in series. Resonant frequency, we have Z equivalent equals to R plus J omega C plus 1 over J omega C. Sorry, I meant J omega L before in case I misspoke. So we say resonance is when the imaginary component of ZEQ equals 0. So we say omega L minus 1 on omega C equals 0. And as per before, this gives us our standard resonance frequency formula of 1 on root LC. And what this equals, if we go ahead and take a quick peek at my previous working, it should be like 100k radians per second. Now, quick note, radians per second, okay? We're working with omega right here. Very easily to mistake with frequency. Just make sure you keep your units consistent and you'll be happy. This, if you double check against your previous lab, when you divide 100 by 2 pi, you get something like 16. So 16 kilohertz-ish. All right, that's part 1. Bam, that's an easy, very nice 3 marks that they've gifted us. So question 2, we see 6 marks. We can typically extrapolate from that and say this is where most of the hard work is going to be. But don't worry, if you need more paper, put up your hand, ask. But yeah, do your best. And yeah, go about it methodically. Let's do this. So, half power frequencies and bandwidth. Okay, so first things first, I need to know what my full power is to determine my half power, right? So P max equals P resonant, right? Because ideally that is where our imaginary component of our impedance has disappeared, and therefore when we take magnitudes, we're only taking the square of one thing as the other square goes to 0, okay? Okay, so let's write this out. Equals, we say V in squared onto Z Thevenin, well sorry, not Z Thevenin, ZEQ, and this will be at resonance, so I'll say omega 0, okay? So V in, that's going to be a magnitude of 20. Mind you, I'm using V in squared on 2 because I'm looking at it, I have a sinusoid, it's not in RMS. And so I say 20 squared on 2 times, and ZEQ at resonance is just going to be my resistive component because all my imaginary impedances have disappeared. So I have R. And when I calculate this, let's double check. wow, it's a really nice number. It is 1. That makes things a lot easier. So, and the reason I say that is just because now, when we go ahead and say P omega H equals P omega low equals 1/2 P max, it's just equal to 1/2, right? And so, taking these into account, I'm going to now calculate for omega through this transfer function, okay? Rather this function right over here, where I use Vn squared over 2 ZEQ, okay? Mind you, power max, something I didn't specify, which I probably should have, is I'm using magnitude of S, right? So this right here, this is the thing we're looking for power, okay? It is complex power, that is how this thing goes. So we use this magnitude of your complex power, your apparent power, as the basis for this, okay? So we say 1/2 equals Vn squared, 20 squared, on 2 times, we're going to use the magnitude of R squared, magnitude of R plus J omega L. Mind you, it shouldn't be ZEQ, it should be Z conjugate. It shouldn't matter too much just because we're taking absolute values. So we would actually have it looking a bit more like this. Don't forget the absolute value. There we go. We calculate this, we push forwards, we end up with 200 over square root of R squared plus 1 on omega C minus omega L, all squared. All right? We can keep working this through, and we're going to try and equate this to 1/2. Now, we want to find omega. We see 1 on omega and omega. It's likely we're going to be turning up with a quadratic somewhere. So what we'll do is we're going to try and get rid of this square root sign. But first things first, let's go ahead and push everything around, do a little juggling act. So we're going to chuck the 1/2 onto the right-hand side and the denominator that we have over here onto the left-hand side. So we end up with root R squared plus 1 on omega C minus omega L all squared equals to 400. All right, and now with that in mind, we can square and then rearrange. Let me just double check. Yep, okay. So square, rearrange, square root, we end up with 1 on omega C minus omega L all squared equals to 400 squared minus R squared. We're all right squaring this. It's just notable that we have technically introduced negative solutions for this because we've amplified the power of omega. Anyways, enough math talk. Let's go ahead and solve it. We take the square root of everything. Don't forget your plus minus. So we end up with plus minus. Actually, I'm not going to put the plus minus over there. I'm going to put the plus minus on the other side. Equals plus minus square root of 400 squared minus R squared. Now, we see omega over here. We understand, oh, well, we know that the half power frequency isn't going to be omega is 0. That's an assumption. That's what we're going to take because it's somewhat reasonable. We're going to multiply everything by omega here and work it through into a quadratic. So what we end up with is omega squared L is going to be chucked onto the right-hand side. You do plus minus omega times the square root of 400 squared minus R squared. And then you do subtract 1 on C. And this equals to 0. Okay, following so far? It's just a lot of math bashing when we need to determine these things from basis. Yep.
When you're doing half of P max, what are you saying there with the S?
Yeah, so P max, it's technically not P max, it's like S max. Just because typically we would actually just compare transfer functions. So you'd have h of j omega, fantastic. The square of it is going to be proportional to your power, right? So that's the typical trick we use. So we would actually usually compare square of the magnitude of our transfer function for voltage. But what I've done here is a very similar thing where I'm actually just comparing magnitudes of S, your complex power seen by the load. Sound good?
So we're using complex, or like the apparent power, not
Pretty
the
much.
average one.
Yes, yes, not the average one, which is why I felt the need to correct yes.
How come Px is Pmax is equal to 1? I'm not
Yeah.
clear on that.
So Pmax, we went ahead and we subbed in according to our power equation that we saw earlier in this crash course. And so that's where we go v squared onto z conjugate, right? So we look at z conjugate, we say, oh, at maximum power, it's just resistive, so I don't need to worry too much about it. V was 20, so 20 squared onto divided by 200 is 1. It just works out to be 1 in this case. Yep. Fair? All right. Good stuff. So we end up with this. We go ahead and do our quadratic. We end up with a whole mess of omega equals. Remember to take into account your minuses and your pluses. This thing, 400 squared minus, and now we can sub in, so 200 squared, this would have been my r squared, plus minus square root of r squared, 400 squared minus 200 squared, and then we plus 4 ln c. Ln c actually turns out to be like 10 to the 10, no, 10 to the 6. But, I mean, ln c, let's just do that. Divided by 2l. You'll notice that this thing becomes massive on the right-hand side. I'll actually just get rid of this line. Yep, the right-hand term becomes massive, the left-hand term is significantly smaller. So if we want two positive frequencies, we've got to make sure that we keep the positive sign on the right-hand term, and then we can let this vary on the left-hand term. So that's just picking our solutions that lie within an acceptable range, okay? As long as that makes sense. We all happy? All right, we're doing ELEC. Be happy, please. All right, so we worked this out, chuck it into your calculator. Somewhat straightforward. Mind you, the reason that we needed to go through this arduous calculation was noting that the quality factor, oh no, the quality factor was less than 10, okay? Since the quality factor was less than 10, it means that our peak is very broad, okay? Rather broad, okay? It's a comparative term. And because it's rather broad, it doesn't have necessarily the nicest symmetry, okay? You might even have resonance over here, and then, oh no, it's not symmetric, can't just do half of that jazz. All right, so double checking that thing can make your life a little bit easier, but anyways, I digress. You should end up with about 118.8 k radians per second as your omega higher, and omega lower should give you about 84.2 k radians per second. Okay, that is for you to double check. Yeah, so I end up with a pretty nice day.
So with that third last line there,
Yes.
is that implying that a few steps are being taken between the line above it? Or
From here to there.
Yeah, what's the process?
So this is just the quadratic formula. So,
Yeah.
yeah, we're just applying quadratic formula with respect to omega. Okay, so that's all. Yep.
You mentioned something about taking the plus, and I didn't hear that very well.
Right. Okay. Yep. I'll just reiterate. So you'll actually find we have two plus minus sets here, right? And that gets a little bit messy at times, but right here we just need to account for magnitudes. So what I would do in this scenario is I take this term, just go ahead and fully flesh it out. Mind you, that is a 200 squared. I'd fully flesh that out and see what magnitude it is, write that down. Then I'd fully flesh out what's on this right-hand side, flesh it out, put it down, and then I'll be able to see, oh, I get something like 2,000 over here, and I get something like 400 over here, right? Now, this isn't necessarily going to be completely indicative, but I can see the 2,000 is much bigger than the 400, So if I want omega to be greater than 0, then it means I need to pick this value, the 2000, to be positive, and then I can plus minus my 400 to get two frequencies that are above 0. Sound good? Yeah.
And in the same way, sorry.
All
in
good.
the same way, if the first term would give a greater value, then it means that you take the first term to be positive and then you plus minus.
Exactly, exactly. So it's making sure that you keep omega within, the positive range. Good stuff. Thank you for asking. Now, that is fantastic. We now need to determine bandwidth. So, we can kind of see that my writing size has exponentially increased. Let's dial it back a little bit. So bandwidth. How do we calculate bandwidth? Omega higher minus omega lower equals our bandwidth. So using that calculation, we can very confidently go and say something like, let me double check my notes, 34.6K radians per second. All right, and then the final part of the question, which we go ahead and validate. Yes, we've found half power frequencies. Yes, we've found the bandwidth. We need to calculate the quality factor now. Now, quality factor, you might think, oh, wait, couldn't I just series quality factor this? It gets a little touchy. It gets a little touchy at certain circuit scenarios. This is a nice estimate, I must say. However, we actually get something a fair bit off, especially since, I'll just write it over here. 3, we do omega 0 on bandwidth equals quality factor equals 100 on 34.6, what was it? It was, and this is about 2.89. If we did that series Q factor thingy, we would get something like 5, which is ways bit off of 2.89. So it's a bit of an estimate. Yep.
Just a question for what's the first file? Because I see like a half power stuff there. Like half equals to the formula.
Yep. So we've gone ahead and said half power is equal to omega, and this is omega as a half power frequency.
So first we found maximum power, and then we divide by 2.
Exactly. Exactly. Good stuff. So we find the maximum power, we divide it by 2, then we recalculate to solve for omega. All good. All good. Thank you for asking. All right, and then let's go ahead and look at the last bit of tedious work, and that's to do with series to parallel conversion. Okay. Now, series to parallel conversion, all it really is saying, okay, at a certain frequency, can I go ahead and, maybe for the sake of my circuit diagram and loving to work in series resonance or parallel resonance, can I change this one bit in series to this one bit in parallel, which might simplify my circuit a little easier, okay? And so it's just saying, oh my gosh, the ZEQ is the same on both from nodes A to B. And the way we can actually just nicely derive this is we look at this little formula here. Let's say I want to go from series to parallel. I go ahead, I say, okay, series to parallel, I want to calculate for my parallel values, right? So I need to divide it into real and imaginary components. So I just realize the realize the denominator. So I get RS minus J omega LS all divided by RS squared plus omega squared LS squared. And then I just divide this across RP. So this gives me RP equals, that should be a square, that should be a square. Yep. RP equals RS squared plus omega squared LS squared all divided by RS, yada yada, okay? Now, we're gonna go ahead and do a very cool question with respect to series to parallel conversion, okay? And we can see it's very, very special because we have this resistor in series with this inductor. And to easily calculate the, more easily calculate the resonance conditions, we can just do our series parallel conversion and then be happy. Now, I might note that it is not necessarily easier to calculate these things, or not necessarily necessary, but it's Did I say necessarily necessary? Anyways, let's just keep doing this. So, first things first, I actually want to be very careful here. This omega 0 is not actually referring to this omega 0. It's a quick thing, but it's actually referring to omega 0 being approximately 1 over root LC, okay? So that's Q coil. We're going to put our answers in terms of Q coil, and that's, while I was doing the working out for this question, I came to this conclusion. It was a little bit, just not the nicest, but anyways, we can rewrite this to go ahead and clear it up. So Q coil is actually going to be equal to root L on root C times RS, okay? And that's just talking about my stuff over here. Now, very cool thing now with Q coil, which allows me to do both of these questions somewhat easier. I can go ahead and just determine RP and LP, because I look at my circuit, I want it to look something like, let me just draw this out real quick. I want to turn this into 2 resistors, an inductor, and a capacitor all in parallel, right? Then I can just use my parallel resonance stuff and I'll be on my way. So this right here will be RP, this will be LP. Now, how do I go about this? I need to go ahead and say, oh, RP equals RS squared plus omega squared LS squared. Mind you, this is omega 0, so it's our resonant frequency, because that's where I want to operate this circuit. All divided by RS. Now, we can also go ahead and say, okay, can we express RP as a multiple of RS? Now, this is where it gets a lot nicer. We multiply and divide everything by RS, so we end up with 1, because that's our first term, and our second term becomes omega 0 squared LS squared on RS squared. Now, this might not look the most neat right now, but if you take a little peek at before, oh my gosh, it's just the square. So we say RS equals 1 plus Q coil squared, right? Fantastic. Now, that may not be immediately relevant, but I'm also going to do the same thing with LP. LP equals to RS squared plus omega 0 squared LS squared all over LS. Is it omega squared LS? Yeah. Now, I can go ahead and once more multiply and divide everything by LS to express LP as a multiple of LS. So I get equals LS outside of RS squared on omega 0 squared LS squared plus 1. There's a little trick here as well, and we say, oh, wait a minute, that's the reciprocal. And so we say equals LS 1 plus 1 over Q coil squared. All right. Okay, good stuff. Josh, can you just double check to see if there's any online comments? Yeah, would be good. All right, now, technically we haven't answered the question at all just yet, but it will be reviewed in due time. And I think just this stuff right here, very, very relevant, okay? I've not led you astray. So, we need to determine omega 0 actually, okay? And we can tell that the actual omega 0 is going to be equal to 1 over the square root of LP times C. Okay, it's not necessarily going to be LC, because L over here is in series, okay, and it's no longer our original circuit. So, what can we do? We can try and express LP in terms of LS, which is what we had before. So we end up with 1 over root C, and then 1 over square root of LS. And square root of LP is just going to be the square root of this here, okay? So we chuck in L, 1 plus 1 on Q squared coil. And now we can go ahead and, wow, it kind of just falls out of there. Square root 1 over square root of 1 plus 1 on Q squared coil. Make that mess. All right. So, how do we feel about that question? that was rather straightforward, as long as we were able to conceptualize the scalar multiple workings of parallel to series. Okay, so it's really just adjusting our components, which was a very cool thing. Now bandwidth, if we take a little peek down here, we can actually understand that, oh, bandwidth equals F0 and Q. We knew that, that's fantastic. And Q is equal to omega 0 CR. Okay, now this is fantastic because I can, mind you, this bandwidth, I can put it in radians per second or frequency. It doesn't really matter, so I'm going to take bandwidth in terms of omega 0, radians per second, to say that bandwidth equals to 1 over CR, okay? Because it's equal to omega 0 on Q, Q is omega 0 CR, okay? So that was the methodology right there. 1 over CR equals 1 over CRP. Now, mind you, we're using, actually, not just RP, it's RP parallel R.
Oh, I've already got a question from the chat.
Oh, okay, what is it?
I don't get how doing this will help us make the resistor parallel to lambda.
Ah, okay, so we go ahead, and we got to just, it's a fair bit of conceptual work, okay, just for online viewers. So we're looking at these two nodes here. We got these two elements in series, and we want to make sure that we want to analyze this in a bit of a parallel notion. So we got to find an equivalence to turn it into parallel. And that's what our series to parallel conversion is, right? It's that bit of juice that gets us the way there, okay? We go ahead, break it up into two, and so the circuit looks like, I'm going to scribble here, breaks down over here, inductor over here, and then capacitor as per usual. And we can see that, oh, wait a minute, that's all the same node, so yes, everything is now in parallel. I hope that clears things up, but yeah. All right, now, before I waste well, not waste, but chew up too much time, we go ahead, we say, okay, bandwidth equals 1 over C times RP parallel R. We want it in terms of RS though. So we just substitute back, and crazily enough, we know that RP is just a scalar multiple of RS. And in fact, it's just by 1 plus Q squared, right? Q coil squared. So we just write it down, 1 over C times R parallel to RS 1 plus Q coil squared. Bam. And wow, that is identical to what we had been asked to show. So good stuff. And yeah, it's just a cool piece of moving forward, converting between series and parallel just through equivalent impedances. All right, we have a summary table here just for your benefit in case you wanted to double check your notes from there. And yeah, I guess I'll be handing over to our other fantastic presenter today, welcoming Jackson. And yeah.
Thank you, Otto. All right, so first thing first, congratulations, you made it halfway through the crash course. We've got 3 more topics to go. I understand that Fourier transform and magnetically coupled circuits are the 2 topics you've done most recently. So you might not be too familiar with it, so I'll try to go a bit slower with it. And if I am going too slow, please let me know. All right. So jumping into Fourier series. The Fourier series is essentially a way of describing any sort of time varying signal into a sum of a DC component and an infinite sum of an AC component. And the reason we want to do this is such that we can use phasor analysis to apply this to circuits. Cool. So to go through the basic definition, this A0 term is our DC term here, and our AN and our BN represent our AC coefficients. It's also important to note that the fundamental frequency is given by 2 pi over the period of the signal. Cool. And these are all the different ways that you calculate each of those coefficients. When can and should we use Fourier series? Basically any time when we have a periodic signal that isn't already AC, because the whole point of this is to convert this into something that is in terms of AC signals. Cool. We don't have time to do an example on these, but it is important to note the other forms of Fourier series. So we have amplitude phase form. The name's pretty self-explanatory. We have DC component plus amplitude at the front, cos, and then in the argument we have the phase. Exponential form, we have only one coefficient, but it is notoriously harder to find compared to an and bn, and then just that exponential there, which represents each of our sinusoids. So that brings us to symmetry considerations. This is probably the part that I want to emphasize the most in Fourier series. So if you see from the table, a lot of these coefficients end up being 0 depending on the symmetry we have. And this will save you a lot of time in the exam if you stop, take a moment to look at the symmetry of your signal and think, does my signal apply to being odd, even, or a half-wave symmetry? Cool. So I won't go through each of these, but we will be applying it in the examples. Just to explain what a half-wave symmetry means, we're basically taking this top signal and it's simply a mirror reflection about the x-axis or the t-axis. Cool. Sweet. All right. So jumping into an example.
A question.
Yeah.
Question about the symmetry.
Yeah.
So in the quiz we did for this topic, one of the questions had half-wave cosine. Yeah, you said half-wave cosine function, and it was solved with an even symmetry, but I was thinking if you solved with a half-wave symmetry.
Okay, I think by half-wave cosine, you're looking at something like this, right? Where you have just the top half of the cosine wave. Was that what it looked like?
I don't remember.
Okay. I think it's called half-wave because they've rectified it. In other words, they've removed half of the wave. They've removed the negative part. But if you look at the shape of this signal, you can see that the left side and the right side of that vertical axis, they're completely symmetrical, right? So that's why in that case you would call that even symmetry. Does that make sense? Cool.
Another question as well.
Yeah.
How do you identify the symmetry of the object? Because one problem I realized I had for the quizzes was I was struggling to find what symmetry it was if it wasn't clearly stated that this is the symmetry for it.
Okay.
Because there was one question that had like a sawtooth, but not this kind of sawtooth. It was just the top parts all put together, and I couldn't really tell what symmetry it was.
Okay. Well, does even symmetry make sense, firstly? Like, it's just a reflection, right? So then if we look at odd symmetry, if I am a bit unsure about it, something I do is I'll start from the middle point, and following it positive, the negative should move in the exact opposite direction as the positive. So this moves exactly opposite, and then if we keep going, this would move down, whereas this would move up, and that would keep continuing. So that means it's odd. In the case of a half wave, yeah, I would suggest trying to check whether this negative side is just a reflection of that positive side there. And if you're unsure whether it's odd or half wave, you can always do the same thing. That goes up 2 and then right by 1, whereas if you go to the negative region, you go down by 1 and then left. So they're obviously not the exact same. Does that clear it up, like how you differentiate? Cool.
Thank you.
No worries. Good question. All right. Okay, so jumping into an example, what kind of symmetry is this signal? Half-wave? Odd, right? It's not exactly half-wave. Half-wave would look more like this. You would have half of the wave here, and then it would be half of the wave reflected like that. So that would be half-wave symmetry. In this case here, we have odd symmetry. Again, we can check by moving in the opposite direction, and we find that I'm following this signal around exactly the opposite way. So it's definitely odd. So in the case of an odd function, we have a0 equals 0, an equals 0, and then we will apply this equation here to find bn. Cool. So we have bn equals 4 on t, the integral between t on 2 of f of t sine n omega naught t dt. Cool, so an important thing to note with this one, this equation here, is that we're integrating for only half the period. So it says in the question here that we have a period of t equals 8, so this would be 8, so then half our period would be 4. Integrating between this region, we can see that for half of it it's 0, between 2 and 4, and between 0 and 2 we have an amplitude A, which in the question is stated as 2. So I'll just translate that into this equation. So we have 4 over the period, which is 8, integral between 4 and 0, but for between 2 and 4 it's there's no signal, so I'm just going to go between 2 and 0. The function is at 2, between 2 and 0, and then sine n omega naught t. We should also note what omega naught actually is in this question. So omega naught is given by 2 pi on t, where t in this case is 8, so this would be pi on 4. Cool. So moving on, we have 4 over 8, which simplifies to a half, and I can bring that 2 out from inside the integral to cancel everything out. So we just have the integral of sine n pi on 4t dt. Integral of sine is minus cos, and we need to bring out the derivative of the argument, so we have 1 on n pi over 4. Integral of sine is negative cos, and that gives us this expression. Simplifying that, I'm just going to flip the fraction on the bottom so that we have 4 on n pi. Subbing in t equals 2, we have minus cos n pi on 2, sorry. And then we have 2 negatives cancel out to be a plus, and cos of 0 is simply 1. Cool. So that is our bn.
Since n pi on 2 is always 0, we can get rid of it.
Sorry, could you repeat that one?
Yeah, cos of pi on 2 is 0.
Cos on pi on 2 is 0, but that n will change because for each harmonic n is like 1, 2, 3, 4.
Oh, true.
Right? So we have to keep that one there.
Yeah.
No, that's right. Cool. So I'll write that down. So our f of t is now a0, which is nothing, plus the sum from n equals 1 to infinity of bn, which in this case is 4 on n pi, 1 minus cos of n pi on 2. And then we have sine n omega naught. I'll replace omega naught with pi on 2 or pi on 4. And that is our Fourier series for that signal. Does anyone have any questions about how I derived that? Cool. Alright, moving on. So like I said earlier, the whole reason we're doing Fourier series is so that we can apply it to a circuit. So now that we've expressed V in as Fourier series, next thing we want to do is, if we have a circuit, we want to convert it to the frequency domain, analyze it to find the output in terms of omega and V in, and then we're going to use superposition to find the impact of each harmonic and its contribution towards the output. So applying that to a question, first we have part B, which is sketch the amplitude spectrum of IT from part A up to the 5th harmonic. So jumping back up to this equation that we had here, just going to take this. Whoop. Cool. And we'll down in part B. If it wants to load. Paste. Cool. So it asks for the first 5 harmonics, so I'll just sub in n equals 1, 2, 3, 4, and 5. For n equals 1, we have pi on 4 and pi. Cos of pi on 2 is 0, so we just have multiply by... Whoop. Josh, can you just check that the stream's still up? Sorry. Yeah. Cool. Multiply by 1, and then that is multiplied by sine pi on 4t. And we're going to keep going. So this is now 2 on pi here. But then we have, this is actually negative 1, so this is also going to be a 2. 2 times 2 equals 4. We have 4 pi again. Sine of n pi on 4t. Pi on 2t, sorry. And we're going to get rid of this n, because n is 2 in this case. And we're going to keep going. I'm not going to explain every single one. I think you get the idea of what's going on here. The fourth harmonic is going to be 0, because in that case we have cos of 2 pi, which just gives us 1 minus 1, which is 0. And then we have 4 on 5 pi, sine of 5. Ooh.
Jackson, the stream's lagging a lot. I don't know if that's a problem with OBS or...
It's probably my laptop, to be honest.
Probably your laptop.
Yeah, that can't be helped. As long as it's still running, I think that's okay. Cool. So we have this expression here. So that is n equals 1, 2... Oof. 1, 2, 3, 4, and 5. Plotting that. So the amplitude spectrum, we're just going to take the magnitudes of each of these harmonics at each of their frequencies. So we have a peak here at pi on 4, an equivalent peak at pi on 2, peak at pi on 3, pi on 4, nothing at the fourth harmonic, and then we have a final peak at 5 pi on 4. On 5 pi. Cool. So that in this case would be the amplitude of the signal with respect to frequency. Cool. Does anyone have any questions about that plot that I just created?
Is it in terms of frequency or angular?
Oh, my bad. Yeah, it would be in terms of angular frequency. So this would be in terms of omega.
Would that be 5 pi over 4, which was the last one?
Oh yeah, sorry, that didn't come through on the laptop. Sweet. And this would be pi. Cool. Alright, so then looking at part C, if it loads. Cool. Calculate the voltage Vt in the circuit using up to the first 3 harmonics only. So luckily we have these 3 harmonics already written out for us, so we're going to use those to analyze this circuit. First things first is we need to find an expression for Vt, and that will have to be done in the frequency domain. So jumping over to this question, we have, I believe it was it's a current source, I of t, and we have a resistor in parallel with a capacitor. So this will be V of omega, this will be I of omega, this was 10 ohms, and this was 2 farads. So to find the voltage across those components are in parallel, so I'll combine them and then just use Ohm's law to find V omega. So we have V omega equals the current so that's in, multiplied by the 10 in parallel with the 2 farads, which I should be writing as 1 on j omega c, and in this case c is 2. Cool. So simplifying that, we have I in multiplied by 10 on j omega 2 over 10 plus 1 on j omega 2. That gives us, multiplying by j omega 2 on the numerator and denominator, we have 10 over 1 plus 20 j omega. Cool. So now we have this expression. We need to sub in each of the harmonics, which is annoying. So I've prepared answers for this question. Just here. Cool. So for n equals 1, we have v of omega equals our first harmonic multiplied by the angle. I'm going to express sine as -90, and just noting that I'm going to express my final signal in terms of cos. Cool, so that is I in multiplied by the transfer function that we've found, where omega is pi on 4. Cool, and that would give us 0.81 with an angle of minus 176.336 degrees, and we would repeat that for each harmonic to follow. So in this case, we would have 4 on pi, -90. Same thing, but in this case, omega is going to be pi on 2. We're going to have 0.405 with an angle of -176.96. Lastly, for our last harmonic, we have 4 on 3 pi, -90. Same thing, but we have 3 pi on 4 in this case, which gives us 0.09 minus 178.78 degrees volts. Does that make sense how I've calculated each harmonic there? Just multiplying the input harmonic with the transfer function. So finally, to find our total answer, we need to add these voltage contributions together, which would give us 0.81. I'm going to convert these phases back into the time domain. So noting that I express sine as a -90 phase, I'm going to express cos as a phase of 0. So I'm just going to say cos. In this case, we have pi on 4 as our angle. And then we're just going to keep on adding each harmonic on, and that will give us our final answer. Cool. Cool, so that wraps up the Fourier series section. Did anyone have any questions about those calculations that I did? That made sense? Cool. Moving on to the Fourier transform. So this is the most recent topic you've done. And honestly, that's fair enough if it's the least familiar. Just to go through what it is, basically the Fourier transform is something that we've created so that we can express signals in the time domain that are non-periodic and convert that into the frequency domain. So just like the Fourier series, we want to convert the signal into AC components so we can apply phasor domain, but for a non-periodic signal we can't use AC components, so we found a different way to do that, And the way of doing that is through these definitions. So this first one is your definition of your Fourier transform. And your second one is your, and your second one is your inverse Fourier transform. So the sneaky thing, just to sum up the derivation of these equations, we've basically assumed that our input signal has a period of infinity. So we're saying that a non-periodic signal is actually periodic, but its period is infinity, which is a sneaky thing to do, but it works, and that's how we got these equations. Moving on to special functions. So there's two functions that you'll see a lot in Fourier transform. The first one is your Dirac delta function. So Dirac delta is defined as a peak at t equals 0 of an undefined height, but we do know the area beneath that peak, and the area enclosed by that peak is 1. Which sounds a bit weird because it's just a straight line pointing up, so how does it have an area? I guess a good way of thinking about it is, say I start with a rectangle with an area of 1, and I keep compressing that rectangle to have a larger height, but maintain that area of 1. Eventually we're just going to have one peak with an undefined height, but an area of 1 underneath. Cool. Then our second function is a bit easier to understand. That's our unity step function, which is just 0 for all negative time, and then it jumps up to 1 at t equals 0. So that's time there. Cool. So here are our Fourier transform pairs and properties. I don't have time to go through all of them, but I can tell you these all work. These were all derived from the definitions that we have up here, but they've just been given to us to simplify calculations and make our working out a lot quicker. Important things to note is linearity and scaling. So say I have two functions here, say this function, adding together. That's the exact same as those two pairs in the frequency domain adding up together. Same as if I have two lots of ut, then that's the same as two lots of this function in the Fourier, in the frequency domain. Another thing to note is this sampling property. So Inma unfortunately did not include the sampling property in her formula sheet. I do suggest this is a formula that you remember. It's especially useful for when you have this delta function inside an integral. As you can see, it simplifies calculations a whole lot. Just by looking at the time shift of this delta function, the answer to this integral is simply f of t, where the time shift is subbed into the argument there. Cool. So yeah, we'll see how useful that is in a moment in this question. So part A, if f of t is delta t minus 1 plus delta t plus 1, derive the Fourier transform. So using the definition of a Fourier transform, integral of f of t multiplied by e to the negative j omega t dt. I'm going to sub in what f of t is given as. So we have delta t minus 1 plus delta t plus 1, and that is all multiplied by e to the negative j omega t. Separating that out, we get this expression. So if we jump back up to our sampling property, we can see that this expression here is simply our function f of t multiplied by some Dirac delta with a time shift. So that first integral is simply going to become e to the minus j omega t, where t is subbed in as 1. So we're going to have e to the minus j omega multiplied by 1. And the second integral using the sampling property again, we're just going to have e to the minus j omega multiplied by minus 1 in this case. So that gives us e to the j omega plus e to the negative j omega. This might be looking a bit familiar. You can convert this into a cos using this identity. And that would just give us 2 cos of omega. Does anyone have any questions about that derivation? Cool. So that's a great example of when sampling theorem would come in handy. Moving on to the second Fourier transform. So we're actually given, in this case, the signal in the frequency domain, and we're asked to revert that back into the time domain. So to do that, we'll be needing to use our inverse Fourier transform equation. So I'll write that down in our working. So f of t is going to be 1 on 2 pi. The integral of this should be our signal in the frequency domain multiplied by e to the j omega t d omega. Cool. So with these questions, there's always multiple ways of doing them. And there's not necessarily one that's better than the other. For example, one way you could do this is to first take the derivative of this signal. So you would look at the rate of change of each of these steps. So we have a step down at -2, a step up at -1, a step, so that's a step down at -1 and a step, this is a step up. And we have 2 step downs. So that's one way we could do it. And then these will all be deltas. Like that. And we could use the Fourier transform property of time differentiation. So when we differentiate with respect to time, we actually have j omega multiplied by the frequency signal that we're looking for. The way that I'm going to do it is I'm simply going to use the definition, but I'm going to express this signal in terms of a sum of 2 other signals. Just because if we take it at face value, we're going to have an integral from 2 to 1 at a magnitude of 10, an integral from -1 to 1 at a magnitude of 20, and then an integral from 1 to 2 at a magnitude of 10. Rather than doing that, I'm going to express this as a sum of 2 rectangles from -1 to 1 and -2 to 2. So when we add these two together, we're actually going to get back the signal that we started with. The reason I've done that is because we actually turn that into just 2 integrations. So looking at this first one, we have an integral between 2 and -2 of 10 e to the j omega t d omega, and then our other one will be integral from -1 to 1 of 10 e to the j omega t d omega. Integrating that, we have 1 on 2 pi, 1 on j omega, then we have 10 of e to the j omega t, where we sub in 2 and -2. And then this other one, we have the same thing between 1 and -1. Cool. So that gives us 1 on 2 pi j omega. Bring out the 10 as well. So we have e to the j omega j t times 2, because we're integrating with respect to omega in this case, minus e to the j t minus 2. Cool. Moving from here, I can see that we have a subtraction of 2 exponentials that have powers in opposite polarity. So that tells me that I can probably convert that in terms of sine. So if we recall, sine theta is the same thing as e to the j theta minus e to the minus j theta over 2. So I'm going to apply that right here. We have 10 on pi omega out the front, and then we'll have e to the j2t minus e to the minus j2t plus e to the j, sorry, again these should be t's because we're integrated with respect to omega, so we're actually subbing in the omega and getting rid of it. So we would have something like this with our 2j underneath. Cool. So now expressing that in terms of sines, we have sine of 2t plus sine of t. Sorry guys, these should actually all be t's. Cool. And last but not least, we can actually express these as sinc functions. So we have 20 on pi multiplied by sine of 2t over 2t plus 10 on pi multiplied by sine of t over t. And that will give us 20 on pi sinc 2t plus 10 on pi sinc t. Alright. Does anyone have any questions there? Yeah.
Why don't we take the integral range from 2 to -2 and 1 and 1?
So that is because of the way that I've split up this signal. So I've expressed this step in the middle as a separate function that's been added on. So I'm just taking the integral of that rectangle and that rectangle separately, and I'm adding them together at the end. Cool. How are we for time? Alright. I might have to skip one of these questions in the interest of time. We'll go to this one here. So sketch the amplitude and phase spectra of f of t equals sine t plus 3 cos t minus 2 sine 3t. First things first, to plot the spectra, this needs to be in the frequency domain. So I'm going to convert that using the Fourier transform pairs. So this is going to be j pi t, and that would be 1. This will be a minus. Three pi. And lastly, the minus 2 pi. Just double checking with these. Yep, so these are the two transform pairs that I've used. So sine of some frequency will become j pi, and then we have two deltas shifted in the negative omega naught and the positive omega naught direction. And then with the cos we have no j out the front, just pi, and then we have the two deltas adding together instead of subtracting. So just correcting this, this should be a plus, and this should be a minus. Then over here, this should be a plus, and this should be a minus. Cool. So to draw the amplitude spectrum, we just need to take the magnitude that's sitting out the front of each of these functions. So for a shifted frequency of -1, we have a peak of pi. I'll make that a bit smaller. And at 1, we also have a peak of pi. at 2, and at 3, minus 2, minus 3. We can see we have a peak of 3 pi, and then here we have a peak of 2 pi. So that would be your amplitude spectrum. Your phase spectrum. So here we need to take into consideration the j that's sitting at the front of these functions. So we have a positive j sitting outside delta t plus 1. So we have a minus 1, we're going to have a positive j, which is a phase of positive 90. And then we have this negative j at positive 1, which gives us a phase of negative 90 here. Continuing that on, we have 0 phase here, because we have 0j, or like 0 imaginary part. And then here we have another j here for the positive component. We have it being positive, and for negative we have it being negative. Cool. Did that phase spectrum make sense? Yeah.
What's the x-axis?
So when we do amplitude and phase spectra, these will always be in terms of omega. Sorry, I made a mistake again. All those t's you see should actually be omegas. Yeah, my bad. Sorry guys. So yeah, these should all be omega. Cool. But yeah, I think the important takeaway here is the phase is found from the coefficients, because those have j's sitting in them. Alright, moving on to amplitude modulation. Emma would have gone through this very, very briefly, because it is not a major thing, but I will touch on it. So amplitude modulation is something we use very often in telecommunications, just because it lets us transmit signals over long distances without them interfering with each other, and also so that we can design antennas to be small and not like a kilometer long. So one thing you might be asked to do is to plot the frequency spectra of an amplitude modulated signal. So this thing here is an example of an AM signal. M of t is your message that you're trying to send. You might be told what this is in the exam. Let's say for this example that it has an amplitude AM and it has a frequency of omega m. So first things first, we would have to simplify this expression. Cool. So we see here that we will get AMVC cos omega mt cos omega ct added on with VC cos of omega ct. Cool. So I've just taken that and multiplied it with the variable at the front. Same with this, I've multiplied it with the carrier frequency at the back. We need to change this into a sum of causes so that we can convert this into the frequency domain later on. Using an identity that you may or may not remember, we're going to halve the total magnitude and we're going to take the difference of these two angles. Cool. So now that they're each separated out into separate trigonometric terms, we can then apply the Fourier transform pair that we used earlier, which was this one here. So we're going to convert cos into pi delta omega plus omega naught, and then delta omega minus omega naught. So this here will be AM VC on 2. So here our omega naught is omega c minus omega m. So we're going to have delta omega minus omega c minus omega m in brackets plus delta, sorry, there should also be a pi omega minus omega c plus omega m, which comes from this next term that we have. Cool. And then we'll keep going. So we have plus delta omega plus omega c plus omega m. We have delta omega plus omega c minus omega m. So that there so that one there is this converted to the frequency domain, and now we just got to convert this. So this is Vc pi omega minus omega c, because this here is our omega naught in this case, plus omega plus omega c. Cool. So that is a massive mess, but you can see that we have 1, 2, 3, 4, 5, and 6 peaks. So when we plot that, we're going to have omega c, which is much larger than omega m. So I'm going to plot these first. So these have a magnitude of, sorry, it's loading. Cool, so this has a magnitude of Vc pi, and a magnitude here at minus omega c. And then we're going to have 2 smaller peaks either side of these large ones that I've drawn in, and these will each have a magnitude of pi am Vc over 2. So drawing that in, we have 2 smaller peaks either side, and this is just going to be omega c plus omega m, omega c minus omega m. Same with here, we have omega c plus omega m, and we have omega c minus omega m. And that has a magnitude of AC Vc pi on 2. Cool. So this is our amplitude spectrum. Cool. So it's not particularly anything new, but it's just applying what we know about Fourier transforms to this signal that we're going to get given in the exam, possibly. Alright, that's enough of Fourier. Last topic is magnetically coupled circuits. In my opinion, this topic isn't too hard as long as you get this very first part, which is the dot convention, which I know can be very confusing. So I'll do my best to just slowly explain how the dot convention works, and then we'll jump into a question. Cool. So the first thing that I want to note is where these dots are, because that represents the polarity of your mutual inductance. Then I'm going to look at which way this current is flowing. We see I1 is flowing clockwise, and it will flow into the dotted terminal of this first coil. So if it's flowing into the dotted terminal of the first coil, that means on the other side we're going to have a positive terminal at the dotted coil and a negative on the other side. Alright, so then we just need to repeat that for the secondary coil. So here we see again I2 flows into the positive, into the dotted terminal, sorry. So then the dotted terminal on this side will be positive and the other side will be negative. Cool. So that tells us the polarity of the mutual inductance. From there, all we have to do is create KVL equations. So for example, following this current through, we're going to have a minus V1 term, which we've just brought over here. and then we're going to have flowing into the positive terminal of this resistor, into the positive terminal of L1. So that's what is seen here, which is the impedance times the current, which gives you the voltage in each case. And then since our current is flowing into this positively marked terminal for our mutual inductance, we're going to mark this with a plus. Does that make sense? Okay. Then for coil 2 we'll do the same thing. So we have a negative V2, so I'm just going to chuck it on this side of the KVL equation. Then we're going to flow from the positive terminal of the resistor, positive terminal of the inductor, which gives us this part. And then again we have the current flowing into the positive terminal of our mutual inductance, which gives us this positive here. In the case where it's opposite, we would have current flowing into dotted terminal here. So we have a positive here and a negative here. Current flows into the negative terminal. So when it flows into the non-dotted terminal, that means that on the other side, this dot is going to be our negative, and this will be our plus. Cool. So then this will be our... Cool. So then this will be our plus, and this will be our negative. So then just going around again, we'll have the same equation, but this time we have a negative, because when we follow this current around, we'll see that it hits this negative terminal first. Same with the second coil. You'll find that they'll always either both be negative, or they'll always either both be positive. So if you do end up with one positive, one negative, just work through your working out again and see where you've gone wrong. Cool. So if you found that confusing, that's okay. I also found it confusing to start with. When you get harder magnetically coupled questions, I find it's a lot easier to use this equivalent model. So basically what you do is you express these dotted terminals as dependent voltage sources. So basically you can forget about which dot is positive, which dot is negative, and it'll simplify your working out a lot more. So just going through this example, the current flows into the dotted terminal here. So then our dotted terminal on the other side will be positive, and the other side will be negative. For I2, your current flows into the negative terminal. So then this side will be positive, and this side will be negative. Then you can see that these pluses and minuses, wait, hang on. Sorry, so this current flows into the non-dotted terminal. So this will be a negative at the dotted terminal and a positive at the non-dotted terminal. And then we can see that these polarities translate directly to the polarities of these dependent voltage sources that we've added in. Cool. And then from that point again, we just do our KVL equations to solve without having to think about which terminal is dotted and which is not. Cool. Jumping into a question. First things first, we need to find the polarity of the mutual inductance. So, current is flowing into the dotted terminal in this case. What does that mean? Positive at the dotted terminal and negative at the other. Here we have it flowing into the negative terminal, so we'll have a negative here and a positive here. Cool. Next thing we would do is we would write KVL equations corresponding to each mesh. So for this first equation, we have current flowing into the negative terminal of the voltage source, so we have minus 100. Then we have flowing into a resistor, a capacitor, and an inductor. So I'll just put all those together in brackets. Cool. And then the last thing we need to consider is this mutual inductance. In this case, the current is flowing into the dotted terminal, so the mutual inductance will be positive. So we're going to have a plus J10. And very importantly, this isn't going to be I1. This is going to be the current of the other source. So this is going to be the current of I2 equals 0. Cool. Repeating that for the other mesh. So this is 1, 2. The second mesh is a lot simpler. We have the current flowing into the 20 ohm, the J15, multiplied by I2, and then again we have this current flowing into the negative terminal of the mutual inductance, so that's going to give us minus J10 I1. Cool. So it's asking us to find the load current IL, which is equivalent to our I2. So I'm going to try and get rid of I1 first, doing these simultaneous equations to save me some work. So we have I1, moving that over and dividing by J10, we have I1 equals 20 plus J15 over J10, I2. And then I'll chuck that into this equation up here. So then we have minus 100, 0, plus 8, minus 12.4 plus 12 is minus 0.4. And then we'll replace this I1 with what we calculated here. So that will give us, if it wants to move, that will give us 20 plus J15 on J10 multiplied by I2 plus J10 I2 equals 0. Then rearranging for I2, I'll bring this voltage source onto the other side, and then we'll just group each of these. So that will all go here, and then I'll bring that underneath. Yeah. Cool. So then that's 8 minus J 0.4, 20 plus J15 on J10 plus J10. And that gives us an answer of 3.46 with an angle of 67.2 degrees amps. Cool. We are 10 minutes over. I will go through this one and then we'll do one last question, which is a bit more challenging, and then we'll wrap up. So, calculate the average power absorbed by the 20 ohm resistor. The equation I'm going to use here is simply P equals half magnitude of the current squared R. So half times the magnitude of the current, in this case was 3.46 squared times 20, and that gives you around 120 watts. Cool. So some other things to note in magnetically coupled circuits. You can calculate the instantaneous energy for just the coupled coils, not for the whole circuit, using this equation. You should note that this is all with respect to time, because it's instantaneous. And each of these inductances are not impedances, they are in terms of henries. When we have coils in series, if the current flows into both dotted terminals, we'll have plus 2M, but if it flows into one and not the other, then we'll have minus 2M. Lastly, we have the coefficient of coupling K. Coefficient of coupling basically tells you how coupled your two coils are. So if you get a K of 1, that means that your magnetically coupled coils are basically maximally coupled, whereas if you have 0, you have no coupling at all. Cool. So I did have some questions here to go through that, but we are short on time, so I will move on, but I will upload the solutions to that afterwards if you want to have a look. Alright, so moving on to our harder example. So we can see here that we have magnetically coupled coils, but this time they're not exactly separated. We have this branch here, which is influenced by both currents. So like always, the first thing I'm going to do is I'm going to find the polarity of each of these dotted terminals. So we have I1 flowing into the dotted terminal of I2. So that will give us a positive here and a negative on the other side. Now we need to figure out which way the current is flowing through this middle branch. So here there's not really any right or wrong answer, but I'm going to assume that I1 is greater than I2, and hence the current is going to flow down the branch with a current of I1 minus I2. Cool. So here we can see the current flows into the non-dotted terminal of this magnetically coupled coil. So we're going to have a negative here and a positive here. To make this look a bit simpler, I'm going to use the equivalent model that we talked about earlier. So I'm going to convert this circuit to a 5 ohm, the inductor, and then we're going to have a dependent source here. Noting the polarity, we're going to have a negative on this side and a positive on this side. And the magnitude of that voltage source is going to be what we would calculate earlier, which is J omega M times the current of the other magnetically coupled coil. So in this case, J omega M is equivalent to 3J. So this is going to be J3. And the current flowing through the other coil is going to be I1 minus I2. So I'm going to write that as I1 minus I2. Continuing on, we will have another dependent source. It'll be negative and positive there. And then we're going to have J3 of simply I1. Cool. So that completes our circuit. And this was 6J. So now we're just going to apply KVL again. Cool. So we'll apply KVL for I1. So we have 100, then we have 5 plus J2, and the current flowing through those is I1 minus our dependent voltage source. And then again, we're going to assume the current flowing is downwards. So we're going to have plus J6, I1 minus I2, minus this dependent voltage source. Cool. I'll simplify that a bit. So we have, in terms of I1, we have a 5, a J2, a minus J3 and a J6. Oh, and another J3 here. Minus J3 plus J6 minus J3. Those will cancel out. And then we are left with 5 plus J2 I1. In terms of I2, we have a positive J3 and a negative J6. So that gives us minus J3 I2, and we're going to move this voltage source over to the other side. Cool, so that's looking a bit better. Then we are going to apply the same thing to our second mesh. So we're going to have J3 I1 minus J6 I1 minus I2 minus J4 I2. So again, we're trying to find the current across the capacitor in this case. So I'm going to simplify for I1 and then sub that in to find I2. So we have minus J3 I1 and then we have plus J2 I2. So we have I1 equals 2 on 3 height 2. So then we just sub this in, and we would get an answer of I2 equals 26.83, 86.6 degrees amps. And that's our final answer. Cool. I skipped a couple of steps just with the algebra of subbing that in, but really the idea of what we're doing here is there in that working out. Did anyone have any questions about magnetically coupled circuits? Cool. Alright, well, good luck with your midterms. Thank you all for coming. Yeah, if you could scan this QR code if you haven't already, that would be really appreciated, just so we can get funding from ARC to keep running events like this, keep helping you out with your courses. But yeah, that wraps it up. Thanks for coming. That is a good question. Do you have access to the ELSOC? Okay. No worries, hey man.
Send it to them, give like an email.
Yeah, I'm happy to do that. Did you want the annotated version?
Yeah.
Yeah.
But then, like, when I differentiate differential costs, this was the answer they have this.
Thanks you all for listening. Yeah, see you in the next crash course. Have a good one.